The problem from GATE Physics 2012 paper reads as follows. A germanium semiconductor is doped with acceptor impurity concentration of 10 to the 15 atoms per centimeter cube. For the given hole mobility of 1800 centimeter square per volt seconds, the resistivity of the material is. We are given 4 options. This is a multiple choice question with one correct answer. Right, so first we will investigate what a semiconductor is. So in a periodic table, in gray you can see the metals, in yellow you can see the non-metals, in the green it's something called metalloid. However, if you focus just on these two elements, silicon and germanium, these are known as semiconductors. They are called semiconductors because their conductivity is not as high as metals. We know metals are good conductors of electricity and non-metals are poor conductors of electricity. The conductivity of semiconductors like silicon and germanium lies somewhere in between, hence the name semiconductors. However, the most characteristic feature of semiconductors is that their conductivity can be tuned as per the need. So for instance, if let's say this is a group, note this is group 14. So let's say I replace a few germanium atoms in the crystal using let's say arsenic. So what will happen, that note that arsenic is electron rich, right? So what we are doing is that we are deliberately adding some impurity to a semiconductor to create something called extrinsic semiconductor. So this is pure semiconductor or intrinsic semiconductor. They are synonyms. So if we deliberately add some small amount of impurity to a semiconductor in order to enhance its conductivity, this is known as, such a semiconductor formed is known as extrinsic semiconductor. For instance, if I add to pure germanium, if I add let's say some phosphorus, so what I'll get is an n-type. Why n-type? Because phosphorus has more electrons than germanium. What I get is n-type germanium semiconductor. On the other hand, if to pure germanium I add some indium, note that indium is here, group 13 element, which is deficient in electrons. What I'll get is some deficiency of electrons, as can be seen here. So I have replaced one among many germanium atoms, I have just replaced one of them with indium. And note that there is a vacancy. In orange you can see the electrons. There is no electron here. Such a vacancy of electron is known as hole. And a semiconductor so formed will be p-type germanium. So just to summarize, these will be electron rich. And the electrons will be provided by donors. In this case, donor is phosphorus. Donors like phosphorus. This category of semiconductors is hole rich or electron deficient, same thing. And it happens because of acceptors like indium, as we have seen in the example here. So let's get back to the problem now. So we were given that there was an acceptor density of 10 to the power 15 atoms per centimeter cube. Whole mobility was this much, and this is the electronic charge. So we were required to find out that what is the resistivity of such a material. Now we know that the conductivity of any semiconductor can be written as conductivity due to electrons plus conductivity due to holes. Now conductivity due to electrons can be written as number of electrons, number density of electrons times electronic charge times mobility of electrons. And similarly, the conductivity due to holes can be written as number of holes P, atomic density P times electronic charge times the mobility of holes. Now note that this is a p-type semiconductor. In p-type semiconductor, how do you know it's p-type? Because we are given Na, acceptor doping. We know that number of holes is greater than number of electrons. This implies Ne mu E will be less than Pe mu H. Mobilities are not that much different for electrons and holes, so we can what can do is we'll neglect this term. And we'll write that omega, the conductivity, is almost entirely due to holes, which is equal to Pe mu H. Now, what is the value of P? P is the number of holes in the system, and who will provide the holes? The acceptors. The impurity that was doped. So that is 10 to the power 15 times electronic charge, we know 1.6 10 to the power minus 19 times hole mobility we know as 1800. Now, if we do all the calculation, if we do all the calculation, it will come out to be 0.288 ohm inverse centimeter inverse. Now we do know that the resistivity is 1 over conductivity. So, and we know the value of conductivity, which is 0.288. If we plug in this value, we will get 3.4722 ohm centimeter. So yeah, so the option C, we can see that option C matches. So this is the correct option.